All right, so yeah, I'll just get started. Thanks for coming. So today I'm supposed to give you a very brief introduction to quantum machine learning together with Qiskit machine learning module. So I try to make this talk very introductory and accessible. If you have any questions, just feel free to ask. So a bit about myself at the beginning. So I'm a PhD student here studying condensed matter physics. I recently became a Qiskit advocate. So if you're interested in this program, you should check out this link or feel free to talk to me about it. And I also, so in the past summer, I did internship at Agnostic as a quantum algorithms researcher. And I'm currently working on problems on quantum optimization and error correction. And I also have a blog, which I occasionally write some blog posts about QC. So you can have a look at that. Anyway, so, okay, a bit of motivation. So why are we talking about quantum machine learning? You know, without me telling you, you already know that machine learning these days are very powerful. They have proven to be very useful in our everyday life. And machine learning today already uses different processors for, performing machine learning tasks. Such as CPUs, GPUs, and even TPUs, which stands for tensor processing unit. And also there are a lot of specific purpose processing units, which we call ASICs. So that's application specific integrated circuits that are being used for machine learning training, machine learning models. So quantum computers or quantum processors, QPUs, can be thought of as another source of specific purpose machine learning accelerators because it's, a new computing architecture. You can use it for this purpose. So using quantum computers may enable training of previously intractable machine learning models by leveraging the power of quantum mechanics, such as superposition and entanglement. So I get rid of this one. Cool. So the second reason why we're talking about quantum machine learning is that it could also lead to new machine learning models that have not been considered just with classical computers. So I listed some examples here. And we'll look at the first two examples actually today in the tutorial section. So the first one is the quantum kernel methods. So it's an analog of classical kernel methods, such as the support vector machine, if you have heard of it. So basically, it's very powerful for doing classification problems. For example, if you look at this figure here, if I give you like a data set like this, it comes in two different classes. So you want to basically build a classifier that could predict, which data point belongs to which class. Obviously, in the original space, you cannot basically linearly separate these two classes of data. But the idea is that you can build a feature map or feature transformation, which is essentially a function that takes your original data set to another space, such that in this feature space, you can linearly separate out these two different classes. So another big class of quantum machine learning models are these neural networks, or QNNs. This term is very broad. They include a lot of different models. So for some examples include the so-called convolutional neural networks, which is kind of shown here. So again, the classical analog of this would be the convolutional neural network. And then you also have the quantum Boltzmann machine. I don't know why this is always here. So the quantum Boltzmann machine is, again, a neural network model that has only two layers. So one visible layer and one hidden layer and one visible layers. So the likelihood of generating a particular output in the visible layer depends on the Boltzmann distribution in physics. So that's why it's called the Boltzmann machine. And then you also have the generative models that are quite popular these days in machine learning. So one very well-known example is the generative adversarial networks, or GANs. So you also have the quantum versions of it, which is just QGANs. And there are a lot more that you can explore. So when you first got into this area of quantum machine learning, you often, you're very likely to encounter this figure here on the left. So essentially, there are two axes. So on the vertical axis, there's the data generating system, which means that whether your data is classical or quantum. And then on the horizontal axis is the data processing device. So whether you are using a classical computer or a quantum computer. So if we start out from this top left corner, that's the CC, which means that you're working with classical data and also you're using classical computers to process them. So that's really the realm of classical machine learning. But in the context of QML, it typically means that you have some sort of quantum-inspired classical machine learning models. A well-known example is the tensor networks, which was originally proposed for solving quantum antibody systems, and it's proven to be very powerful in doing like classical simulations of quantum antibody systems these days. So moving down, you have the QC regime. So here, the data is quantum, but you're still using a classical computer to simulate or process this data. So this area is basically how you use classical machine learning models to better help understand quantum systems. So now going on top again, you have CQ. So this is really where quantum machine learning comes in, right? Because in this area, we're now using quantum computers. So, and this is typically a synonym for QML these days because we're mostly just working with classical data, but we're using this new paradigm of computing, which is quantum computers, to do what we usually do with classical machine learning. And then moving down again, you have QQ, which means that you're using quantum computers to process quantum data. And this is really the area that you can sort of expect some quantum advantage using quantum computers compared to like classical machine learning models. But this is also an area that's like really hard, and it's an active area of research these days. So, okay, so now I'm going to introduce a few key concepts in QML. So the first one is the so-called variational quantum circuits, VQC for short. So this is really the main method, QML method, for the so-called noisy intermediate scale quantum devices, or NISQ devices for short. So in quantum computing textbooks, we've learned Shor's algorithms. We've learned, Grover's algorithms you've heard on Tuesday, right? So, but the problem with these algorithms is that typically they require a large number of gates to perform some task that you want. So a prime example, again, Shor's algorithm, you need to build a very deep circuit to be able to do it. But this is just kind of impractical in today's quantum computers because they're so noisy, and once the circuit becomes really deep, then you get rubbish, results at the end. So, so people came up with this idea of VQCs. So the idea is that, you have these parameters, variational parameters built into your quantum gates that you can sort of update iteratively. That kind of, allows you to build like shallow circuits that can do, because the thing is, I guess it's kind of bringing the inspiration from classical machine learning, where you have like this deep learning models where you have like variational weights that you can update. You're essentially like doing optimization with the circuits. So the VQCs have similar structures to other modern quantum algorithms. So one example would be the variational quantum eigensolver, which you heard about in, I guess, Wednesday's talk and as well as Thursday's talk. So this is very useful for doing chemical simulations for calculating like ground states of a Hamiltonian. And then the other example would be the QAOA, or quantum approximate optimization algorithm. So that's used for optimization problems. So typically for VQCs, you have these following general steps. So you first prepare a fixed initial state. For example, you can prepare all the states in 0, right, in the computational basis. And then if you're dealing with classical data, then you have to sort of encode this classical data into a quantum state to be able to like run on a quantum computer. So this is what we usually call the encoding or embedding layer. So this is kind of shown by these RY gates here. So This is just like one way of like encoding classical data. You can think of them as like the rotation angles that kind of move your quantum state around the Bloch sphere. But you can design like many different we call ansatz for just this encoding layer. And this is just one simple example of it. And then after you encode the classical data into a quantum state, you have to process it. And the way we process it is to apply a parameterized model. And that's what we call the processing layer. So in the example here, the processing layer is essentially like this part. So you have some RZ gates acting on different qubits, and then you have some CNOT gates to basically invoke entanglement between different qubits, and then RY gates again. So again, in the variational circuit design, you can have essentially an infinite number of ansatz. So you just have to sort of come up with a good one that. So depending on what the problem that you're trying to solve, you have to kind of like try different ansatz and just pick the good one to go with. And then finally, you would typically perform measurements to typically, many measurements to be able to like build up statistics, to be able to like extract observables that you want. An example would be like the expectation value of some kind of operator that you want to know. Okay, so any questions about this slide for now? Okay, cool. And the other concept is the quantum circuit training. So the question here is that, we have this variational parameters, right? How do we train these quantum circuits like we train neural networks in the classical sense? So one of the most widely used methods is, of course, gradient descent. You probably have heard of it, along with many variants of it. So you have the stochastic gradient descent, Adam, natural gradient, and so on and so forth. There's a lot of them. But all of them actually require one very important common ingredient, which is the gradient of the circuit's output with respect to your input parameters, those variational parameters. And to be able to calculate these gradients on a quantum computer is not very easy. Because, so first I'm going to talk about this backpropagation, which is really kind of empowers today's deep learning models. The idea of backpropagation, it's really just a glorified term for like doing the chain rule, because you're taking derivatives and derivatives, right? So the pros of this backprop method is that it has a very nice scaling with respect to the number of parameters. So in today's deep learning models, we're talking about like millions or hundreds of millions parameters. So to be able to like compute these gradients, you have to have a model that have a method that scales very nicely. But the cons of this is that it has to sort of store all these intermediate grade derivatives. And that causes an increased memory usage. So because of this, it makes it very basically impossible to be able to use directly on today's quantum computers, because today's quantum computers are not designed to store any intermediate values. In other words, we don't have QRAM yet, just like we have classical RAM. We don't. So to get around this, people actually came up with this the so-called parameter shift rule. So with this method, you can now compute the function as well as its gradient on the same quantum device. So you don't even need to resort to classical devices. So this is a very simple example, or just illustration of this parameter shift rule. So you have a quantum circuit, right, which is a unitary matrix U. So the output of this quantum circuit is just F, well, we call it F. So the variational parameters are theta here. So in order to calculate the gradient or the derivative of this output with respect to the input parameters theta, what you do is you essentially compute the difference between this function with just the theta plus some shift, basically a positive amount of shift, and then you subtract this one, which is like you move it to the other side, like the opposite amount. Yes.
Good question. You just had mentioned like QRAM and like quantum memory or lack thereof quantum memory. I recall can't remember who it was, but I've heard some conversation before about like the development of quantum memory.
Yeah.
Like so they're working on it, like what exactly is it? And like what are the drawbacks? Like what's potentially happening after, do you know that?
Yeah, I'm not so familiar with this area, but I'd say, well, the thing I know is that it doesn't exist. It
It's just
exists
not
today. Yeah.
used.
Yeah.
It's more research.
Yeah, it's pretty much research at this point. Yeah.
Okay.
Okay, so with this method, another pro of it is that it gives exact gradients, so it's not an approximate solution. But of course, the potential drawback of this is that it scales roughly linearly with the number of parameters. It's not as bad as like exponential scaling. Yes.
Exactly. Is that possible? Because it's still discrete.
Yeah, it gives you, it's actually an exact result. Yeah, so because the thing is like, you know, if you think of like how you build this parameterized quantum circuit, you have a bunch of like rotation gates, right? Ry, Rz. So they could be expressed in terms of like the trig functions. So that gives you, you know, exact results. So yeah, so the con of this is that it scales roughly linearly with the number of parameters. So it's not a problem when you have like relatively small models, but as your model gets larger, like I don't know exactly like how many qubits that, you know, when that's going to become a problem. But eventually when your model becomes large enough, then potentially, you know, you're going to wait for a very long time to be able to compute the gradients. Okay, so the third concept is the hybrid computation. So when people talk about hybrid computations, they sometimes could mean different things. So I'll give you two interpretations. So the first one is that essentially it means like you use quantum computers together with classical processors, such as CPUs and GPUs. And even under this, it could mean different things. So I guess the most the most common meaning of this hybrid structure is that you have some sort of classical optimization loop inside your quantum circuit training. So this is a very nice illustration of what's going on regarding this classical optimization loop. So you have some input. It could be classical data, it could be quantum data. You feed that into your quantum circuit, and then, you know, your quantum circuit will output some you know, whether it's like expectation value of some observable or something else that you want. So based on the output of this quantum circuit, which is run on a quantum computer, you can construct the cost function or the loss function, as you would do in classical machine learning, which is something that you want to minimize, right? So the minimization or the optimization step is actually run on a classical computer instead of on a quantum computer. So that's what we mean by the hybrid. So this is essentially a hybrid loop, right? So because you use both quantum computers as well as classical machines to be able to do this iteratively. But in addition to that, you can use classical computers to even pre or post process quantum circuit outputs. You can even build arbitrarily structured hybrid computation structures. So, you know, it's kind of up to you to like how you want to build your quantum your hybrid architecture. So the other thing that people could mean when they talk about hybrid computation is that even within the, you know, the sort of the machine learning model, the architecture, there could be, you know, some quantum components in addition to the classical machine learning model. So we'll see an example of this in the tutorial, and this is what we call the hybrid quantum classical neural network. Okay, so now let me switch gears. I'm going to talk about the Qiskit machine learning module in particular. So at the bottom here, you have Qiskit. So everything is built on top of Qiskit. You know, from, I guess, Tuesday's talk, you know, Qiskit allows you to build quantum circuits, allows you to apply unitary gates. It also allows you to compute gradients if you have a parameterized circuit. And also it comes with like a bunch of like classical optimizers that allows you to do this, you know, optimization routine. So on top of Qiskit, the QML or Qiskit machine learning module has basically two classes of models. So you have on the right, you have the kernels, the quantum kernel method, which is, one example of it would be the SVM that I just mentioned at the beginning. And then the other class is the neural networks. So under this neural networks, you have 3 different classes of QNNs that you can build. So an upflow QNN is like a general structure for a QNN. And then the 2-layer QNN is like a special case for this upflow QNN. So in the two-layer QNN, you have the feature map, which is the classical encoding layer, as well as an ansatz, which contains all the variational parameters that you want to update and train. And then also you have the circuit QNN. So the difference is that it's quite subtle, actually. The circuit QNN only allows you to sort of samples the final output of your quantum circuit. Whereas, if you're using an upflow QNN or a 2-layer QNN, it allows you to actually compute the expectation value directly. But you can't do that with the circuit QNN. Okay, so building on top of these 2 classes, you now have, for example, for kernels, you have more sort of special purpose classes. So for example, this is the QSVR, which stands for quantum support vector regressor, so for doing regression, and then QSVC for support vector machine for classification. So the same goes for the neural networks class, right? So you have the VQR and VQC, which is variational quantum regressor and variational quantum classifier. And even on top of all these, there's a very nice integration with PyTorch in Qiskit machine learning, which is called the torch connector. So that allows you to basically use PyTorch, which is a very famous classical machine learning library that's written in Python, to do all this, optimization. Again, we'll see an example of this with code. Okay, so I'll show 2 examples today. So I'll give some background to each. So example 1 would be the kernel method. So the one I'm going to introduce today is the support vector machine, or SVM. So essentially, if you look at this data here, so you have this data come in 2 different classes. I label them -1 and +1, so which is blue and red respectively. The idea is that you want to basically build a classifier, which means that you want to build this linear decision function that will allow you to predict, when a new data point comes in, to predict which class that it belongs to. Right. So mathematically speaking, this linear decision function is a sine of some weights times your your input data x minus b, which is the intercept. Right. So it's just a linear function. And the objective of building up this SVM is to basically maximize the margin. So the margin, if you look at the figure on the right-hand side here, the margin here, basically you want to draw a line between all this, your training data points that can sort of maximize this margin. So if you work out the math, the margin is actually equal to 2 over the modulus of W, where this W vector is the vector that's perpendicular to the line that you draw. Okay. So, again, mathematically, it means like minimizing the W modulus. Okay. But more importantly, it's minimizing this W modulus under this constraint. So the constraint says that for each data point, I, so the label of it, yi, which can be -1 or +1, times this function, the linear function that's inside your decision function, should be greater than or equal to 1. So that's the mathematical statement of SVM. Okay, so but you see that in this vanilla SVM that I just introduced, you can only basically separate or do classification for linearly separable data. But what if you have some data that look like this, right? So you have one class of data in this circle, inside the circle, and then you have some the other class that's like outside. So this is clearly not linearly separable. You cannot just draw a straight line to separate them. So what do? So people come up with this idea of doing a nonlinear feature transformation, which we call feature map. So again, mathematically, basically it's a function that takes your data, which lives in this Euclidean space, RS, to some other space, right? Depending on the problem, depending on how your data set look like, this space, you have to choose like how you want to construct this feature map. So this space V is, it's up to you to decide. And then the hope is that, by doing this nonlinear feature transformation, even though your data set, like in the original space, is not linearly separable, but it's going to be linearly separable in the feature space. And then another important concept is called the kernel trick. So the kernel trick here is to rewrite the SVM problem to depend only explicitly on these kernels, which are, for two different data points, x and x prime. These kernels can be expressed as an inner product between these two feature functions, phis, right? So the kernel trick is to basically rewrite your problem that only depends on k, but not directly on phis. You may wonder why we want to do that, right? The reason is that typically in most of the problems, a lot of problems, it's easy to compute the kernels, but it's not easy to directly compute what the feature vectors are. Right. So I give you a very simple example, again, with this example illustrated here. It's a two-dimensional data, x1 and x2. So the feature map here is constructed in the following way. So you have a third dimension, which is calculated by doing, x1 squared plus x2 squared. So what that does, in visualization, you can see that basically it moves the original data from a 2D space to a 3D space. So now in the 3D space, they become linearly separable. So you can just draw a plane to separate out the two different classes. So that's, I think, a very nice illustration that tells you why kernelized SVM is useful. And going to quantum SVM, and this is just gonna emphasize the point that I make regarding the kernel trick. So you will see that in quantum SVM, it's actually very easy to compute the kernels. So in this case, the feature map is defined as a quantum circuit, which I call E of X, and X is your input data. So this E, which is a quantum feature maps, again, takes your classical input that's in the Euclidean space RS to some other space, which I label as, S. So S really means the, density matrix, the state where density matrices live in. So, for individual data points, let's say you have a data point X, what this quantum circuit gives you at the end would be some quantum state, right? So you can represent this quantum state by constructing this outer product of the wave functions, which is the essentially the density matrix. So now if you compute the quantum kernels, you see that, okay, without going through all the math, you see that basically it's the expectation value, or the, the technical term will be the Hilbert-Schmidt inner product. But, if you look at the final expression here, right, it's basically just the expectation value of these two operators together. So the first one is the feature map Hermitian conjugate. So E dagger on, one of the data points, X prime, and then you have the feature map itself on a different data point X. So in quantum circuits, it's very simple. It's just, like this, right? So you first apply a feature map, which you know how to construct, and then you apply the Hermitian conjugate of it, but with a different data point as the input, right? And then at the end, you do the measurements, which allows you to basically compute this expectation value that allows you to calculate the quantum kernel. So if you have a data set that has like many data points, right? So you could imagine like for each pair of these data points, you can have a kernel value. So that allows you to construct a kernel matrix. Okay, any questions regarding the first example? Yeah.
What was the name of the anyway?
Okay, so going into the second example is the hybrid neural networks that I said I'm going to show. So this is based on this tutorial, or one of the lectures in Qiskit textbook. So there's the link here. You can check out later. But essentially, this is a simple illustration of like what's going on. So a hybrid neural network, as the name suggests, it's just a classical neural network, but with some quantum circuits in it. So on top, you have some classical nodes, which we call, we just call them classical nodes because like in classical machine learning, when you have this deep learning models, you typically have like multi-layer structure, right? So for each layer, you have like multiple nodes. So and then the output of this classical node is going to be fed into the quantum node. The quantum node is essentially a quantum circuit. So you could do like classical data embedding, right, with the quantum circuit, and then you process it with the variational circuit. So the top layer, because it's classical, you can do it in PyTorch. And the second layer, because it's a quantum circuit, you do it in the Qiskit. And then after that, it gives you the output from the quantum circuit, which you can process. You can construct the loss function, which you want to minimize based on these outputs. And then you can do the optimization again on a classical computer with just PyTorch, right? So here's a more concrete representation of what I just showed. So let's say, in the classical node, you have a 2-layer neural net, very simple. And in the first layer, which is the input layer, you only have like 3 nodes. And then the output layer has 2 nodes. So how you get the outputs H1 and H2 is by doing essentially like linear, what do you call this? Like you have some adjustable weights, which are these W's. And then I guess I could draw it here, right? So you have X1, X2, X3. So you can see that for H1, you're gonna basically assign 3 different weights. So W1, X1 plus W2, X2 plus W3, X3. But with just this, it's just linear function. It's not very powerful. So what you do is you have some kind of nonlinear activation function, which I call sigma. So this sigma function can be, has different forms. So for example, this could be sigmoid. It could be what we call redo. Could be even the pinch function. So the choice of this nonlinear activation function depends on the sort of the range of the output that you want, right? So I can't remember exactly, but for example, one of them would take the output to be in the range of -1 to 1, and some other would take the output to be the range of 0 to 1. So once you have this nonlinear activation functions, you get these outputs H1 and H2, which you then embed into your quantum circuit, which is in the middle layer here, right? So what's actually missing in this diagram is that you have these processing layers even in the quantum circuit that I mentioned, which contains all the variational parameters that you want to sort of iteratively update. So after doing the encoding and processing, you do the measurements with the quantum circuit. So you have the results from measurement 1 and 2, which is then fed into another classical neural net, which has only 2 nodes, right? And then it gives you, so again, a 2-layer classical neural net. The final output layer has only one node. That's your final result. So this is more or less a simple diagram for how we construct the hybrid neural network. Any questions? Yeah.
Over classical neural network scan?
Say that again.
What advantages does this approach give over just pure classical network scanning?
Well, it depends on the problem, right? I can't make a very general statement about this. The reason is that even with like today's quantum machine learning, we don't really know like what kind of advantages that quantum circuits would provide. Although like people are talking about it, but no one actually really knows the answer. But it's kind of expected. I mean, because with quantum computers, you have this properties like superposition and entanglement. So maybe in this regard, it could provide some certain advantages, but it's not clear. But with this, we're just saying, there's a way that we can incorporate quantum computers even in classical machine learning models. And and you can run it and see if you get better results or worse. Okay, so let's go to the code. Okay. Okay, so as I mentioned, can you see it well enough? Okay, good. So as I mentioned, the first example would be this quantum support vector machine for classification. So what you do first, you do some necessary imports. We're gonna use the scikit-learn package for you can import SVC, which is the support vector classifier from scikit-learn, because we want to compare the quantum SVM to a classical SVM. So, and then you're gonna import some from Qiskit. You're gonna import some modules classes, also from Qiskit machine learning. So first you set up this quantum instance. So here we're using the chasm simulator, which is a noisy simulator. We're specifying the shots, which is like how many measurements you want to do with each time with your quantum circuit. So that's like over 1,000 shots. Okay, so next we generate the data. So this data is actually you can generate it with this function that's coming from the Qiskit machine learning module. So it's called the ad hoc data. So this is just a helper function that allows you to plot the data, and let's see what the data looks like, right? So this data has two classes, so A and B, right? So, and the hollow ones are the training data, and the solid ones are testing data. So I think if you go scroll up here, so the training size will be 20 for each class. So in total, you have 40 training data. The test size is 5. So in total, you have 10 for two classes. So this is a binary classification problem. So with scikit-learn, you can very easily to build a classical kernel or classical SVM model. So what you do is you just call basically SVC from scikit-learn. You have to specify the kernel, or maybe you don't, because I think it defaults to RBF. So RBF means radio basis functional kernel, function kernel. It's a very commonly used kernel for SVMs. But you can also specify other kernels such as linear, poly, RBF, sigmoid, even pre-computed. I don't know what that means, but anyways. Yeah, so after you build this SVC, you can call svc.fit, and then you give your training data and the training labels. And then you can, so this is what essentially it's doing the training in the back, right? And then you can evaluate your model by doing svc.score, and then you feed in the testing data, the testing feature, the test labels as well. So you see that with just classical SVC, it gives you a score of 0.4, which is not very good. So now let's move on to the quantum version, right? So in the quantum version, remember how we build the quantum SVC is by doing is by essentially, let's see, employing this feature map, right? So the feature map is essentially this data encoding layer. So there are two feature maps that I used for this demo. The one is, and they're both built in Qiskit machine learning. So the one is the Z feature map. So if you plot it by doing, Z feature map dot decompose dot draw, you see that essentially it's basically this Hadamard gates at the beginning, and then you have P gates. So the P gates are the phase gates in Qiskit. So they are essentially the RZ gate. So RZ gate is, if you think about like the state on the block sphere. So what this does is that, say, if you have a state, so that's your z-axis. So if you have a state that's like this, right, it's a quantum state on the block sphere, then what this RZ gate does is basically rotates it around the z-axis by a certain angle. So it comes with an angle. So this is your brief parameter in the parameterized circuit. So you can even write it out in matrix form. So this is going to be, so actually, let's do, this is actually the exponential of minus I, minus I over 2 sigma z, which is the power of the operator. So if you write out a matrix, it's I think e to the minus I theta over 2, 0, 0, e to the I theta over 2. Right, so that's essentially what this P gate is. And then here I'm using like 2 layers because you don't have to just limit yourself to 1 layer, which you can see here. Here I call the repetitions to be 2. So that's why you're seeing like 2 repetitions for this. So the ZZ feature map is essentially, building on top of this Z feature map. But, after the P gates, you have this additional structure, which is the C0 gate, and then another P gate, and then another C0 gate. So what this is actually, E0, and then you have V, theta, E0. This is actually this gate. So this gate is the well, we call it RZ. That's why it's called the feature map. Also, if you look at like the P gate in this, right, you see that the argument that it takes is actually composed of both x0 and x1. So unlike the other P gates, and the reason you want to put this C0 gates is because you want to basically create entanglement between these 2 qubits. Okay, so with the QSVC, from Qiskit machine learning, you basically do the same as you would do in scikit-learn. You do dot fit with the training data, and then you do dot score for the test data. And you see that the quantum SVC with the Z feature map gives you a score of 0.7, which is slightly better than the classical one. But now if you involve the ZZ feature map, it's actually 1. So that's pretty good result. You can also call predict to basically, so you feed in the test features, and it's going to tell you what the prediction of the labels are. So any questions about the kernel method? So it's very simple in code, because a lot of things are basically done in the back of Qiskit machine learning already. So, okay, now let's go to the more complicated example, which is the hybrid QNNs. And we're going to do this MNIST classification. You probably have heard of MNIST. Basically, they're images of like handwritten digits from 0 to 9. So we're going to use the torch connector function in Qiskit machine learning. So we're using PyTorch here. So you have to install PyTorch and import a bunch of like functions from PyTorch. Again, we have to initialize the quantum instance first. And here, instead of using the one that we used before, which is the QASM simulator, we're using a different simulator this time, which is the state vector simulator. Okay, so first you load the data, and to do that, we use PyTorch. And also because we also want to limit ourselves to a binary classification problem, so we're only going to use images that comes with the label 0 and 1 and not others. So we're excluding all the others. And we're using so 100 samples for each, so there will be 200 training samples. You can even inspect the shape of your training data. So you see that basically you have 200 samples, and each image is a 28 by 28 pixels image. So that's like 784 if you convert it to one-dimensional vector. Okay, you can also plot them, right? Plot a few of them, so you have some digits with the labels on top. So I don't think you can see very clearly. Let me just change it to a light theme. Yeah. Okay. So you can see the labels on top more clearly now. And then you could do the same for the test data, right? You load it from PyTorch again. So you use data loader from PyTorch. And here we're using 50. So together would be 100 test data sets, data points, sorry. Okay, so now we can define our QNN and also the hybrid model. So remember, to create this QNN, you have to build a quantum circuit. And we're using here the two-layer QNN that I talked about. So two-layer QNN, so the first layer will be the feature map, which is the data encoding layer. So we're using the ZZ feature map as before. And then the ansatz, which is the variational parameterized circuit, we use the so-called real amplitudes one. So this is what this ansatz look like. So you have RY gates, right, with two parameters, and then a CNOT gate to induce entanglement, and then another set of RY gates. Again, I'm using two layers. That's why you're seeing kind of two repetitions. Okay, so in the two-layer QNN, you specify the number of qubits, which is 2, and then feature map ansatz that you specify on top. The input gradient, you have to set it to true to be able to train it later on. So that's very important. And then what it measures at the end would be the AR Pauli expectation value, which is essentially the expectation value of the Pauli Z operator. So you have 2 qubits. So what you would do, what it measures is actually, so how would be the first qubit, how would it be for the second qubit? So the output from this quantum circuit will be a 2-dimensional vector. Okay, so you just combine them, so you can plot them. Kind of, you can see, the ZZ feature map as well as the ansatz. Okay, so now you have the quantum component ready, and we have to incorporate that into a classical neural net. So you can build a classical neural net with PyTorch. So this is very standard for PyTorch if you have any experience with PyTorch. So you will inherit from this PyTorch module class, nn.module, and then you can specify what kind of layers you want in your architecture. So let's build some convolutional neural net. So I have 2 convolutional layers, and then dropout, which is also very standard in ConvNet. And also I want some linear layers as well. So this is the fully connected layers that are just like linear layers. And then we have the QNN, which is a quantum component. So I use torch connector from Qiskit machine learning with the input QNN that I just built on top, right? Which is, this function here. Okay, so and at the bottom here, you have to specify essentially the feed forward path. Again, this is telling basically PyTorch how you want to construct the neural net. So first you have the conv1 layer, so you have some convolutional layer 1, and then you would do an activation, which is this ReLU activation function, and then you do a max pool. So in case you're not familiar with convolutional neural net, I'll give you some simple examples. So let's say you're dealing with 3x3 image data. Right? So what this convolutional layer does is that so you have to select the size or the size of the kernel. For example, if I choose the kernel of size 2x2 like this, and then you also have to select the so-called filter. So let's say, I don't know, 1, 2, 4, 3, 5, 6, 8, 9, 2, something like that. So basically for each pixel, you have certain values, right? And then you have to define the filter that has the same size as your kernel which is 1/4 if you convert it to the vector. That would be, I don't know, 0, 1, 0, 1, right? The choice of the filter is up to you. Like if you want to sort of pick out, let's say, some vertical features, then you have like one way of doing that. But if you want to pick out like horizontal features, you would choose a different filter. But this is just like one simple example. So what you would do is now, so this is block convolution. You would do the inner product or the dot product of this filter vector with this kernel. So that's essentially 1.2 plus 1.0, 2.1 plus 3.0 plus 5. Right? So that's going to give you 7. So that's what you get out of this block from this convolutional layer. So at the end, it's actually a 2x2 image. And the first value here is 7, as we calculated in the product. And how you get this 2x2 is that you kind of move this, you have to specify the so-called strike size. So let's say if my strike size is 1, then I basically move this block to here. So my second block is this, my second kernel is this. And then you do the same with the same filter, you calculate the inner product, and that's going to give you, another number, 1. And then you move down, like, and then you have like this kernel, the same. This. So at the end, you get like 2x2. That's how you do the convolution in a conv neural net. What max pooling does is like, if you have like this, and again, you have to specify the size of your max pool. So let's say if you have 1, 2, 3, 4, and then when you do this, you do a max pool, and you can't see that. So it's going to give you, basically, it takes the maximum number from this block. So 4, right? And then you do the same for this, and then you get again the 2x2. So that's what max pool does, potentially. Okay, so again, you have another convolutional layer with another activation function redo, and then you do another max pool, which is kind of complicated. But okay, even after that, you apply 2 linear layers, right? You have the fully connected 1, fully connected 2, and finally you apply the quantum circuit, the quantum the QNN, right? And because our QNN has only 2 qubits, so it's very important that the output of your last layer should be 2, because you only have 2 qubits. And that's why you're seeing, the FC2, which basically takes an output dimension of 64 to down to 2, and that's when you can feed it into your quantum circuit. Okay, so at the end, you can basically work out, so you can build up this hybrid model, which is net of QNN, and then you feed in one of the training examples, for example, right here. It's gonna give you the output, which has 2 values, because it's measuring like 2 expectation values, right? And then you can do the training. So this is again very standard in PyTorch. So inside training, you have to specify the training epochs, which here is 10, and then you have to initialize the gradient, which is by doing 0 grad, and then you call the model, which is your forward pass, calculate the loss, and then you do backward pass, which allows you to do the backprop in PyTorch, and then you update the parameters based on all the gradients stored here by doing .step. And then this is what you see kind of as your training goes on, right? As the number of steps increases, your loss is decreasing. And then you can even plot it if you store all the values of the losses. So you see that it's decreasing and kind of plateaus. If you have like more number of training epochs, then it should kind of plateau to a certain value, which means that it's doing its job. Like the training is kind of successful. You can now save your all these model parameters for your trained model. And then you can load it if you want to basically do tests now, basically see how successful the training was. So for tests, you're doing the testing data, of course, and then you can calculate the loss, the average loss, and the accuracy. So in this case, we're getting like 100% accuracy. But remember, this is like that there are not many testing samples, and we're only limiting ourselves to just binary classification problem. But this is kind of shows you how to build your hybrid network using PyTorch as well as Qiskit. Yeah, so that's pretty much it. Questions? All good. Awesome. Thank you.